pleasure to invite and to introduce Jiayuan Mao from MIT, who's going to talk about neurosymbolic concepts for robotics manipulation. And she's online. Let's see if we can hear her.
Oh, can you hear me?
Yes, perfect.
Okay. Can you all see my screen also?
We can. All right.
Okay, cool. Okay, so let's get into it. So thank you for the introduction and good morning, everyone. I'm so sorry that due to some visa issues, I'm not be able to come in person for this talk. But today I'm going to talk about neurosymbolic concept for robotic manipulation. So I'm going to start from, one of the important goals in robotics, which is to have robots that can do a lot of tasks across different domains. So for example, we want to have robots that can clean the room for us, that can cook for us, that can brew tea for us, and do these things across many environments, for example, in the field, in different houses, or in schools and hospitals. So learning a single goal condition policy to do everything in many different environments can be very challenging. So one of the ideas that we have, a promising direction, is to combine model learning, reasoning, and planning to achieve this kind of goal. So before we talk about the actual method we're going to use, we want to first talk about what should we learn and how should we combine them together. So let's try to first draw some inspiration from human perception and reasoning. So if you look at this thing in this image, as humans, you can instantaneously recognize there is concepts in this thing. So for example, we understand that there are objects and there are object properties associated with the object. For example, we understand the first object is orange and the second object is not. We also understand there are relational concepts such as the object A is left out of object B. And furthermore, we have those kind of action concepts that describes how the agent can do to change the object states and their relationships. So we're going to call this kind of concept representation neurosymbolic concepts because there are symbolic aspects of it. For example, we have their syntax, we have their semantic form, and for actions, we have their preconditions and postconditions. So very importantly, those symbolic aspects of things tell us how these concepts can be combined together to form more complicated concepts. And in order to finally connect them to visual perception and physics, we also need additional neural network modules. For example, for classifiers, for object properties, for relationships, and also policies for actions. So by combining those kind of neurosymbolic concepts in various ways really allows to solve a lot of problems in physical reasoning and action. So for example, we can answer questions, we can write image captions about 2D images, we can understanding the dynamics of events and also understanding causal relationship between events in videos, and we can do similar things in 3D things. And of course, we can do manipulation tasks by combining all those concepts. So today I'm just to focus on the robotic manipulation aspects of these neurosymbolic concepts. But before we really talk about the actual algorithm we're going to use, I'm going to quickly revisit some of the key aspects of this kind of neurosymbolic representation we're going to learn. So we want to make sure that, first of all, they are compositional. And second of all, we want to make sure that those representations can be learned from relatively little data. And third of all, we want to make sure this kind of representations support fast reasoning and planning. So speaking of robotic manipulation, the overall framework I'm going to use today is based on this idea of task and motion planning for robotics. So given the input state and some instructions, for example, put all food items into the fridge, the robot can first perceive the initial state of the environment, extracting object properties, their poses, and also their relationships. And first of all, generating some kind of task level plan. In this case, contains 4 steps, like open the left fridge, remove the pot lid, and move cabbage, and also move the potato. And we call this part like a task planning part. And furthermore, the task level plan can be further refined into a motion level plan, in this case, composed of also 4 steps, but composed of actual robot motion. So there are really 2 kinds of basic elements in the task and motion planning framework. So first of all, we have some kind of predicates, such as is food or relationship predicates. And for each predicate, there will be corresponding classifier associated with them, trying to infer them from visual perception data. And second of all, and more importantly, we want to have some basic operators that we know the robot can do. And for each operator, it's important to understanding the preconditions for them, the effects for them. Basically, these 2 parts corresponds to the transition model of this operator. And then, for example, in this like a pick and place action, it has like several arguments. We say we want to specify what's the object I want to move from which position to another position, and what should be the grasping we're going to use, and what should be the trajectory of my movement. So in order to generate all those continuous parameters like grasping poses or trajectories, we need additional like samplers for those continuous values. We want to have grasping samplers. We want to have trajectory samplers, for example, RT planners. And of course, based on the sampled parameters, we want to have finally controllers that can actually move the robot to achieve the certain goal. So this kind of base operators usually directly models the object that is in contact with the robot. So this diagram kind of summarizes what we call the domain specification in task and motion planning. It composed of predicates and classifiers, parameter samplers, and the transition models. And based on that, we can develop different kinds of discrete and continuous domain planning algorithms that takes the input state and also the goal as input and try to generate what's the next action to take for the robot. So this kind of framework is pretty general, but when it comes to implementation, there will be a lot of difficulty choices to be made. So for example, if you want to think about how to open left fridge door, we need to reason about where to grasp, how to move myself, how far should I open? For the pod lid, we need to understand, where to grasp, where to put it. Will there be any side effects? For example, if the pod lid is very hot, we need to be careful about placing it. The similar thing is true for moving cabbage and also moving potatoes. So again, our final goal will be to develop some algorithms that can solve all those kind of problems for many different objects, for many different tasks, and across many different environments. So my proposal I'm going to talk about today will be trying to do learning to tackle all these challenges. So we start from this observation that task and motion planning is a pretty general framework. But however, manually programming everything can be very challenging, especially when we are trying to deal with perception and continuous parameters. So we are interested in using learning to tackle these challenges, in particular, learning some kind of neuro-symbolic representations for objects, relationships, and actions. So here is how we're going to formalize the learning problem. So we're going to assume that we have some knowledge about some set of base operators. So this base operator contains, actions like pick and place or pushing objects. These actions are pretty general, and arguably they can be very hard to learn them from very little data. But after human engineered it, they're going to be very, very general. So we'll be thinking about the idea of specializing these operators to do very concrete tasks, like specializing the operator of pick and place to do painting, to use different tools, to execute pouring, to open articulated objects, and also placing objects or sorting objects in receptacles. So let's talk about, based on this definition, then what should be the objective of learning? So there are two aspects of learning we need to think about. The first one is for this kind of specialized operator, we need to learn additional transition models, basically additional preconditions and postconditions for those actions. So on the top right, I'm showing you this like a synthetic robot domain. It's called like a paint and a sort. So in this domain, the robot can move object into some specific colored balls, and there are painters which will paint the object into the designated color. And then finally, the agent needs to sort them in the final box. And similar thing for tool using, for example, in order to learn how to use a hook to reach for a distant object, you need to understand what should be the target object movement model. And a similar thing for pouring, we need to understand the state change happening to the object in hand and also the object that you're pouring into. So of course, in order to finally execute all these actions, we need additional samplers. So for example, for hook using, we need to understand, trajectory. We need to learn additional trajectory samplers that can, synthesize trajectories for actually moving the hook. And also for sorting objects in different scenarios, we need to learn additional samplers for placements. So in many cases here, you can see that we don't need to learn additional controllers, but only, these transition models and samplers, which is good for us. So the first talk I'm going to talk about today is called PD Sketch, Integrated Domain Programming and Learning and Planning. So we have seen so far manually programming everything for a task and motion planning framework can be very challenging. So however, it is worth noting that humans are particularly good describing some qualitative, structural, and causal aspects of a domain. And machine learning algorithm can be good in learning detailed parametric model for things. So at the end, we want to get great generalization from just very little training data. So to concretely ground these ideas in a concrete domain, I'm going to, go back, revisit this like a painting and a thought domain. So here we have our state space composed of the agent poses, the object poses, and their visual perception data, which is an image crop of the object. We can define as human, different predicates on it, like object A is next to another object, with the object shape properties, the object color properties. And also we want to have additional transition models like pick and place actions. So the learning target one will be the classifier for all those predicates. We want to learn, how to classify object colors and shapes and the relationships. And for relationships, we also need to learn additional samplers so that we know how we can place an object from one location to be in another receptacle. And second of all, we want to learn additional transition models, basically how we should get object painted. So the high-level idea in PD sketch is that we want to combine human sketch of the transition model and learning. So here I'm showing this concrete example of specializing this pick and place action into a painting action. So here I'm saying the additional effects of this painting action is that for object B, if the object is inside B and also some condition is true, here I'm using this question mark F to denote some gap, some slot that I want to fill in with neural network learning. And this thing will, if this condition is true, then the object property will change according to some rule, which is also unspecified by the human, but we know it's going to depend on the current status of the object and also the object O and also the object B. So how we can combine this kind of sketch with learning? So the high-level idea is I want to translate those kind of symbolic program into an actual computation graph. So given the current state composed of object poses and also agent position and also visual perception from the objects, the first thing I'm going to do is we're going to evaluate those classifiers between the object O and also each other object for both in and this question mark FC. And then we're going to do a conjunction of the output of these two classifiers. And finally, based on the output from these classifiers and also this question mark G prediction of the next object state, we can predict what's the next object state from the current state and also the current action being taken. So during training time, in a self-supervised way, we can observe, what's the next object state in the next time step, and then use that as a supervision for the predicate for the predicted object state. Because the entire competition graph is end-to-end differentiable, so we can just directly leverage backpropagation and a stochastic gradient descent to update the models. So concretely, so each of the question marks will be implemented as a small neural network module. In this work, we just use simple MLPs to do that. And then human will sketch out the overall structure and we use machine learning to fill in the gaps. So this is for the transition model part. So in the next part, I'm going to talk about how we can learn continuous parameters in a very similar way. So let's think about specializing this action of pick and place into another action called like a place an object into another receptacle. So the process of generating parameters for this action composed of 3 steps. The first one is want to get, what's the current position of the object that we're going to move. And second of all, we're going to sample the target location of the object. And based on the starting location and the target location, we're going to call some kind of like RT sampler to generate the trajectory. So here, we're going to focus on just the learning part for the sampler for the relationship in, because for the second part, the trajectory part, we can just leverage, existing collision-free motion planners to do that. So the high-level, model for those sampler model looks like the following. So the input to it is the shape representation for the object O and also the receptacle, and also the pose and orientation for the receptacle. And output of that will be a sample from some distribution of the object O, so that the object O is inside the object receptacle. So this entire model can be implemented with any specific generated model. So for example, you can use diffusion models or use VAE to do that. And in PD sketch model, this kind of samplers are learned from expert demonstrations because we kind of want to avoid, exploration in continuous spaces. So before we talk about, the different applications of this method, we first want to, study from a machine learning perspective, whether this kind of like combining neuro-symbolic representations actually give us better learning and planning efficiency. So here we are going to combine 3 models. The first one is the PDS-ROB. It contains, just manually specified human robot movement models. The only thing it needs to learn additionally are those like object classifiers. And the second model contains some abstract robot description, contains a bunch of holes inside it, specified a human, but the machine learning model need to fill in these holes. The third model is just like a plain, object-centric like an object-centric transition model learning method based on graph neural networks. So we're going to compare them in 3 aspects. So I'm going to go through them one by one. So first of all, if we look at the data efficiency for learning the transition model, we can see that from just a very small amount of prior knowledge, we can significantly improve the data efficiency in the model learning aspects. And as you can imagine, this kind of better performance in model learning accuracy also translate better into the actual performance of the task. And sort of, and arguably more importantly, those kind of neuro-symbolic representation, because they are kind of like a factored composed of objects, properties, and relationships, they actually allow us to use domain-independent heuristics computation to improve the planning efficiency compared to models that does not use any kind of symbolic structures in their model. So I'm not going, due to the time, I'm not going to talk about the details, but the high-level idea is you can generalize some classical AI planning heuristic computation into this kind of neuro-symbolic representation. So now I'm going to show you some examples like a planning using the learned model and also continuous parameter samplers. So here on the left, I'm showing some like training environments. We're going to train this model on this like a painting and sort domain with certain kind of goals, like a painting 2 objects into the designated color and sorting them in the target box in some particular way. And after learning, this kind of model can directly be applied to new scenarios with a different number of objects, with a different kind of goals. In this case, the goal is for X, and we want to paint X to be yellow, and we want to sort them in the box. So we have been talking about this idea of PD sketch, which is basically a framework that combines program sketches and machine learning to learn this kind of domain models for task and motion planning. And it uses those neuro-symbolic orientation to improve data efficiency in learning. And also it leverages the symbolic structure in the transition model for faster planning. However, as you can imagine, learning everything from scratch can be relatively unscalable. So I'm going to later talk about, concrete ways that we can, leverage those kind of neuro-symbolic modularized system to enable learning from different data streams. So due to time limits, I'm not going to talk about this work in detail, but just briefly mention the high-level idea for our 3 different projects trying to tackle the learning problem for each 3 parts in this diagram. So I'm going to start from predicate learning and classifiers. So the high-level idea is that we want to leverage some sort of like pre-trained vision foundation model for predicate and classifier learning. So let's look at this like simple, tabletop manipulation task where the goal is we want to put the heart into the hole. And there are really, 3 different aspects in the instruction that we need to reason about. We need to reason about the spatial relationship in, and we also have, shape properties like heart and hole. So for object properties, actually, we don't need to just like learn from scratch, from some like, robot demonstration data or from self-exploration, because we know we already have like a pretty good visual recognition models, such as like a pre-trained clip model, which is the concrete one that we're using here. We're going to use like a frozen pre-trained clip model to do all the object recognition part for us. But for object relationships, we're going to learn the classifiers and the samplers for those object relationships, because there's currently no, vision foundation models for this kind of things. And here I'm showing you, 2 of the real-world manipulation tasks about like a packing object into the plate and packing the pitch into the bowl. So it's worth noting that the object being manipulated here. So for example, the apple and the peach, they're never seen before during any of the demonstration we provided to the robot. So this kind of zero-shot generalization is directly achieved by leveraging the pre-trained and frozen clip model. So second, I'm going to talk about, how we can accelerate the learning for parameter samplers. So the concrete idea I'm going to explore here is learning from videos. So concretely, we're going to leveraging video prediction and optical flow estimation, trying to reconstruct object motion in manipulation videos. Either they can come from, teleoperation or from just like human hand manipulation. So this kind of idea will enable us to learn from video datasets for samplers for articulate objects, like how to open a door, or for different tool using actions. So the overall, pipeline looks like the following. So given the input, go, which could be the output of the task level planner, and also the current state composed of the RGB image and the depth map. The first step we're going to do is that we're going to do a video prediction, basically synthesizing a video that hallucinates how a robot or a human might be able to accomplish this task based on the current initial configuration. And second of all, we're going to apply an existing, optical flow estimation model, try to reconstruct the object motion in this video, in the synthesized video. And finally, we're going to combine the synthesized flow and also the depth map to reconstruct the human pose trajectory in this video. And based on that, trying to solve for robot commands by using, inverse kinematic solvers or, RT planners. So the third idea I'm going to talk about is how we can accelerate the transition model learning. So the high-level intuition is the following. So we have seen so far the model, like PD sketch, it really leverages those kind of like symbolic structures, some kind of like a code definition for the transition model to improve, data efficiency during learning and also planning time efficiency. So the concrete idea we are going to explore is whether we can leverage large language model to propose those structures to us instead of just asking human programming to write down everything. And we're going to perform learning for the details, such as the connection with the visual perception and also additional samplers for, motion. So roughly, the pipeline looks like the following. We have human instructions in natural language, such as give me a sliced piece of bread. We're going to ask, those large language models, such as ChatGPT, to tell us, to slice something, you need to use a knife. And this can be further translated into some code definition, like in order to slice something, you want to be holding something, and the object you're holding should be a knife. And based after some like learning for details and samplers, we can execute this action, to finally use, the knife to slice a piece of bread. So I've been talking about this idea of like using, neurosymbolic concepts towards building more generalist robots. So here, I want to give like a very quick summary about things we have talked about so far. So I've been talking about this idea of like neurosymbolic concepts and how to combine them through different reasoning and planning algorithms to solve tasks across different domains and modalities. And there are two important aspects of this kind of representation and our learning paradigm, which is, first of all, the modular nature, the neurosymbolic nature of things enables us to do data efficient learning from various data streams and combine them together, for example, from images, from videos, and from text. And second of all, the symbolic structure of the model enables interpretable, but also more importantly, this is something that a lot of time we care more, which is, it enables faster reasoning and planning when actually trying to solve tasks. So here's the end of my talk, and thank you all for listening.
Great, thank you so much. I think we have time for a few questions.
Hello.
Hello.
Thank you for your talk. And my question is about how do you decide the problem of the strict states? Well, for example, you have different ways to put something in the fridge. And as I could understand from your presentation, you are using definite trajectories and poses for the learning. So how you solve the problem that there are many ways to do these tasks with many poses and many trajectories? Thank you.
Oh, yeah, sure. Let me try to go back to this slide. So, so the question is, how we can actually make decisions about, different placements in the fridge, for example. So, of course, when we're trying to move an object from one location to the fridge, there are a lot of things we need to decide. For example, when you decide where to grasp, we need to sample like stable placement for the object. Also want to make sure that if we want to put multiple objects in the target space, we need to understand there are enough space for later items to be placed, and different kind of things. So here I'm really like abstracting out some of the implementation details for things. So if you think about the task and motion planning framework, it really the task level plan really can be refined into a bunch of a lot of constraints you need to satisfy where you are trying to find a motion plan to solve these tasks. So for example, you have conditions like these two objects being placed into the fridge, they should not penetrate each other. Sometimes you have additional qualitative constraints such as the object should be aligned in some ways. So each of these constraints will, the concrete way we're going to do that is for each different constraints, we're going to learn one particular sampler for them. And during inference time, we're going to use smart ways to combine all those samplers together. So as you can see, sometimes if there are many different constraints we need to satisfy, then finding a good sample to continuous parameter for things can be really challenging. And that's still kind of like an open question.
So if I understood correctly, for each case, you have like definite scenario. So if you, for example, I don't know, something don't get to do, to put in the fridge something, you have a case in predicators for this scenario, yeah? I got correct.
Yes, yeah, I think that's basically correct. Yeah.
Okay, thank you very much for your answer.
Thank you.
Yeah, thank you very much for the talk. My question is regarding the uncertainty in the system in terms of the uncertainty in the state of the robot and the objects. Is there a room for this or how do you fit uncertainty within this framework? Thank you.
Yeah, that's a very good question. So for example, if you look at this kind of like tool using environments because of the uncertainty in visual perception and also the uncertainty in controller in actual execution, there will actually be a lot of uncertainty. For example, it's very hard to learn a system that can robustly predict what the distant object will land in. So right now we have not used any kind of like a planning under uncertainty method, although I think that's a very important future direction to go. So the strategy that we're exploring in the earlier paper is that we just do online replanning. So basically the idea is when you're doing task and motion planning, you first just think about how you can generate what's the best first action to take. So for example, I'm going to do some hook using action to reach for a distant object. And then roughly I just make like a point estimation of where should the object land on. And then when we basically plan the rest part of it. But during execution time, after we execute the first action, you reperceive the environment and then see, where's actually the robot and then where's actually the target object. And then basically you try to replan from the updated visual perception signal and starting from there. But of course, in certain kind of the scenarios, it will be very important to incorporate some like a planning under uncertainty method to handle these kind of things.
Yeah, thank you.
Thank you for the talk. I have a question regarding the PD sketch. So after human draw the sketch, there are some ML you need to fill out. So how do you train it? In other words, do you need the expert demonstration to train it? And if yes, and how about the sample efficiency? Do you need to train collect expert demonstration for each skill you want to specialize and train for it? Yeah.
Oh yeah, of course. So that's a great question. So the quick answer is in the paper we talk about here, we did not talk about anything related to self-exploration in the environment. So here, for example, in this figure I'm showing here, so all the data are collected by just human generating expert demonstration for things, and we're just going to compare different models in terms of their learning data efficiency from different amount of data collected by human. So in the paper, we have a certain kind of extension by trying to combine that with, just self-exploration by the robot itself. So you can imagine the robot basically just do self-exploration in environments and try to, learn the model and, and then try to do planning to solve like later tasks. But of course, if the environment is very hard to explore, for example, if there are certain scenarios that are really hard to achieve, then I think some kind of like human demonstration or some kind of like a guidance or reward signal will still be very important.
Gotcha. Thanks.
One more.
First, thank you for your talk, and I'm curious about the T-sketch. So how do you determine if your sketch is optimal, for example, like input, output?
Yeah, that's a good question. So the quick answer is in this project we don't put any effort on that. We're just going to assume that the human programmer he or she is very smart, and they will give us like very good sketch for the domain. So if the human provided sketch is is wrong, then currently there's no way that we can fix that. So, but if you think about the idea of you can later on I talk about this idea of how we can leverage large language models to provide those sketches for us. Then the concrete idea we're going to use there is just asking large language model to provide a bunch of candidates for the sketch definition of an action. And then we're just going to do learning based on that and just pick the one that has the highest success rate in terms of the task completion.
Thank you.
Right. We're running out of time, so we'll have to close here. Let's thank the speaker again.